Hi everyone, I hope you can see me, you can hear me and so on, and the sound quality is good. And so we are all ready to start our next lecture, and our next lecture is how can we do anomaly detection, and in particular, how can we do anomaly detection for sequential data. As for other topics in this course, in a way it's close to what we already saw in machine learning, but also there are some important differences which we will consider later. And also, I think that many courses underestimate the importance of this topic. And also, there are a lot of approaches connected to like older, more classic approaches to anomaly detection and more modern approaches based on neural networks. And I will be happy to tell you all about all this. And so let's start. Okay, the lesson plan is the following. So you'll start with the general intro, with taxonomy of different types of anomalies, on other problem statements related to anomaly detection. Then we will move to how can we do this with the tools we already have from other tools of machine learning, and in particular from deep learning. And we mostly will consider unsupervised or self-supervised approaches for anomaly detection with very few label data. And so we'll describe the general idea of what we can do in this case, and then move to applications to the different models that can be applied to the solution of unsupervised anomaly detection. In particular, we'll consider as the main modern approach autoencoders, and then in particular generative adversarial based autoencoders. In this case, also I will talk a bit about what we are doing right now on this topic and what I suppose will also be interesting for all of you. So let's begin with a deeper insight in what's anomaly detection. Usually we say that we have something very different from the data we have in our training sample. For example, here we have photos of cats for normal data and photo of raccoon as an anomaly. Also, even from this slide, you can see that the problem statement for anomaly detection is quite vague because we can say that these two first types of figures is normal data, and when a cat has a bird in his teeth, it's some kind of anomaly because we have very small number of images with sprays compared to the regular walking in and out cat. And in particular, this data set was collected in an attempt to automatize the door opening for a cat as he approaches the door, and also for punishing him for killing a bird. And so if cat come to a door and a camera sees that this cat has a bird in his palm, then it means that it blocks the door, so he has no access to the inside of an apartment. And so in this particular case, the anomaly was this cat with a prey, and there was some number of images there, but we can for sure consider more broad anomaly detection when you want not particular cats with prey and related supervised problem, which is itself just imbalanced classification problem. Okay, we need specific metrics, but in general, we can use gradient boosting or whatever we have, for example, even deep neural networks because it's an image as an input. And normal data, we want to catch everything else that we don't feel into this set of images, and we can even imagine all possible usage cases for this particular anomaly detection. We can say that we have to identify anything out of distribution. It can be raccoon, it can be some other animal, maybe other cat that's coming to our place, but it's different from this black and white guide, and so on. So if we move to more serious types of problems related to anomaly detection, we can imagine something like this. At first, we say that for fraud detection, we also have anomaly detection, and it's also two types of problem statements. The first type is that we have some part of data labeled with a mark anomaly, and another larger part marked that it's like normal transactions or normal phone calls or whatever. And so we want to solve this imbalance classification problem that's in this particular case anomaly detection problem. So in this case, we again have like a good solution from the beginning. We just have to tune it a bit to get a good result to them. And also we have another problem statement where we don't know what kind of behavior can we see if the transaction or the call is fraudulent. In this case, you just want to say that we have like this two-dimensional distribution of good data, so this normal behavior, and also we have some anomalies out there. They're distant from normal behavior, so we can say that they have large anomaly scores, and we can identify them as anomalies. We can apply similar paradigm to many different cases, many different applies problems. For example, we have an airplane, we have some subsystem of an airplane, for example, air conditioning or engines or something else, whatever. And we also can try to do failure detection. And in this case, we have also anomalies. So we have very small number of labeled true cases. And in general, we don't have breakage in airplanes often. So sometimes we don't even know that something can happen. And we want to know beforehand that some behavior is dangerous because it's very different from the common behavior for an airplane. Also, turning to the last points for intrusion detection, we have like a network, a corporate network, and there can be some DDoS attacks or attacks related to intrusion into this network. And we want to identify this bad behavior with machine learning approaches for earthquakes. The story is also quite similar to what we had, but there is a lot of problem specific that we will not consider here in the course. But in general, we also have very rare events because we are usually interested in like earthquakes with magnitude 6, 7 or more. And we actually, especially if we live in seismic active region, we don't pay much attention to earthquakes with magnitude 2, 3, and 4. And these guys are very rare, actually, it's like about 1% of our samples of all earthquakes. And in this case, it can be quite hard to identify them. And this is definitely an anomaly detection problem, but it is very specific type of input data. And trying to identify what kind of specific does this problem have and what kind of approaches are useful and what are not. I can say that we have typical challenges for all these problems. The first challenge is that usually we need much knowledge that's related to this particular problem because we have very few labeled examples, and so to identify right figures, it's very hard, or right features, I'm sorry. And so we require this problem-specific knowledge because of our lack of data, and it means that in many cases for each new problem, we should invent a new approach, and for this new approach it works, but it's kind of specific, requires domain knowledge, and so on. So, okay, it's a typical scenario, but we will see if we can overcome this kind of problems later. Also, the second problem is that, okay, the problem statement is not very clear. Often we want to identify something that we have very few examples of, or even don't have examples at all, because anomaly behavior is something that doesn't happen too often. And this also leads to the third point, because we actually don't know it's anomaly, it's not an anomaly in many cases. We have like border cases where we want also to do some kind of machine learning. And as we are trying to search something that we have little knowledge about, we are facing a very poor mathematical problem statement. But later, when we will go to models, we understand that it's not that scary, and sometimes we can provide good solutions. Okay, any questions up to this point? Let me have a very short break and 1 minute. So you will answer plus if you understand everything and we can go on, or maybe some questions that come to your mind. And also during 1 minute, if you understand everything, please write down an example problem statement for anomaly detection from your practice or from the practice of your colleagues, or something you came over when you were surfing the internet. So you have 1 minute to complete this task, and then we will discuss some applied problems for anomaly detection. Anyone? Yes, a good example. Okay, yes, subsystem of a gas turbine, and we have like this challenging problem. Again, we have this typical case where we have very small number of anomaly observations, and so on. Okay, maybe I will ask someone to provide an example of anomaly. That would be Alexander Yesin. Oh, okay, he already voted. Okay, for drilling, yes. Ronnie Field medical cards, yes. Regarding earthquakes, I have a few anecdotes about that some earthquakes were predicted before they occurred. It does not mean that we predict exact day when the earthquake occurred. Rather, we say that we have very large tension in this when we view Earth from geologic view, and we can say that during the next 6 months there will be a large earthquake, so you should be prepared, and so on. So kind of yes, but yeah, mainly it's kind of sometimes or often we construct these models with like not something that very dangerous like nuclear plants. Rather, we are trying to construct these models with simpler systems like airplanes. And then it's like kind of we have multiple layers of defense, I suppose. And often catastrophe is something that happens when there is a lot of factors coincide and happen at exactly the same moment. In this case, catastrophe occurs, but often we like don't see too much about it, and so we can say that it's due to machine learning that we can identify catastrophe. But okay, one more example is that when we are talking about fraud detection, we definitely can identify fraud with this kind of methods. So it kind of helps in industry. Maybe not such inspiring experience when we are saying about preventing the natural disasters and predicting them, kind of. Also, okay, we can say about COVID that it was quite obvious from the very beginning that we will have more cases, and all models that were tested were like said at the first place that in some time we will have this kind of disease, so you should be prepared and should have enough medicine, enough medics. Okay, but no one paid much attention to it except Asian countries that kind of have similar diseases in the beginning of 2000s. And also about like growth curve, and that we have some exponential growth, and we can identify it. Classification anomaly detection, we can say that sometimes there is about similar things, sometimes it's different. And so I think it's a good point to start talking about the next slide. So we see that here we have three methods. We have supervised, unsupervised, and semi-supervised problem statement, and all of them are typical for different types of anomaly detection. When we talking about supervised method, mostly we are talking about classification. We can say that we have some, maybe small number of data labeled with a label anomaly, and in this case, we solve imbalance classification problem. So we have a classification problem where we have 99% of example for normal class and 1% of example for anomaly class, and we try to identify between them. And this is definitely a classification problem. But it's not all anomaly detection problems that we have in the real life. Sometimes we even don't know what we are looking for. In this case, we have unsupervised problem, and we just want to find what behavior is anomal and what is not. And we have something in between. Then we have very few labeled cases. For example, it's not like 99%, 1%. It's like we have usually normal data, and we have fewer examples here, 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 and here. For example, identified as anomalies. In this case, we kind of can't learn machine learning models that can happily identify all those cases. But we can try to, for example, construct anomaly score, then select a threshold for this anomaly score. So we construct an anomaly score using supervised method and select the threshold using few available examples, and it's kind of close to classification but different. Also, we can try to create different taxonomy for anomaly detection, and it's about the input data. And here, yeah, we interested in particular sequential data, but again, we have all wide range of possibilities for this kind of approach. And for example, we can say that sometimes we have tabular data. For example, we have like time, and we say that we observe signal from many devices, and we want to identify anomaly on the basis of what we have for many devices. For example, I can suggest that here we have an anomaly because this blue green curve is different, and so we can say that maybe it will be an anomaly. And if you have label, we can do it. And also for structured and semi-structured data, it's important part of our modern anomaly detection, because often we want to identify anomalies in very complex scenarios. For example, we have a series of photos or a video, and we want to say that at some point of the video, something bad happens, and we want to fight this. For example, we can try to identify fire using cameras and say that, okay, it's fire going on, so we should call a fireman here to help with the situation, or it's a flood, or maybe it can be some, we can have a driver, and sometimes taxi driver is very tired, and he is like in between sleeping and driving, and it's a very dangerous situation we want to identify. And in this case, we want to proceed complex data from sensors, or a data from camera, or maybe some smart watches that he is wearing, and we're trying to add all those data to create a final decision. And in this case, we need deep neural networks because we can proceed audio and video signals, usually a series of images, without good representation constructed by deep neural network. And to the last but not the least point, it's often said that we have two possible scenarios for anomaly detection and novelty detection. They are very quite close, and we will explain more about what I mean here. For novelty detection, we can say that maybe it's another object from our distribution that we have never seen before. An example is as a figure where we have like red tigers, and we have this novel white tiger, and we want to say that we have some novelty, and we detect it, and we say that is novelty score for this photo of two tigers is quite high compared to the anomaly score for the tigers we have here, 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 and here. And also we can say that sometimes we observe objects from another distribution, and it is anomalous for our particular case. If you observe not tigers, but a horse or a jaguar, then we say that in this case we have an anomaly and we should detect it, and it is something we also don't see. So in this case we have anomaly detection. I'm thinking that we have like a terminological difference between these two approaches, and most anomaly detection methods are as well novelty detection methods, and it's more about business problem statement, not a mathematical problem statement, but it's often useful to understand that there can be some difference. Also, it's important to take context in the account. We can say that, for example, we sometimes anomalies are not anomalies if we given different context and so on. And to frame this, I can say that sometimes we can say that there is not, we can say point anomaly if you have a particular strange point. But if you have a set of points and each point is normal, but if we look at all of them, they are very strange, and we have group anomaly. I will provide more meaningful example at the next slide. And also it's important to know that sometimes we have contextual anomaly. Okay, this informal example is also good. In this case, we, for example, can see a man in a mask, and in 2019, it's kind of anomaly to see a people in the street that is walking like this. But right now, it's kind of an option for a normal people to walk through the streets in this way. And so when we are trying to move to more realistic problems, we can say that, for example, we have transactions data and we have very large amount of money spent for some particular case. And we can say this point anomaly. But we look further and we see that, okay, there is a very large number of similar transactions. And then maybe a collective anomaly or group anomaly here. Because if we see only one transaction like this, we can see nothing anomalous. But if we see that this is like a pattern here, and it's some very unusual pattern, then we can see that it's very strange. We should do something about this. If we have a time series, we can say something similar. For example, we have like this normal behavior, and then we see that this varies. And again, if we look at each point here, we can say that each point here, 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 and here is completely 100% normal values that we observed in the past here and here and during all other time moments in our cycles. But if we look at this interval as a whole, we see that there should be like something like this. We expect something like this here, like this dashed line. But we see this constant movement, and it definitely an anomaly, if you can read. It also has some relation to contextual conditional anomalies. When we again see some value that's completely normal, if you look as a whole data set, but if you look as a context, we say that it's very strange, and we should try to avoid this kind of thing. So we have a large number of possible problem statements. This is what we should take into account about when we think about real problems. And okay, I think we have time to have some fun and try to identify anomalies at this site. This could be a good practice. And okay, let's wait a bit. I'm opening. The screen. Okay, so we have this example, and let's identify where do we have anomaly here. At what time moment do you think it's anomaly in the data? Yes, good guess. Yes, let's check the answers. The next slide here. Yeah, you can say it's definitely here we have an anomaly. 4,000, maybe two, but okay, it's quite close to what we have at 1,500. So okay, I'm not sure, at least this is not the right answer according to the after the presentation. Let's try another one. Where do you think there is an anomaly here in this problem? Then I think this problem is harder. Okay, so we have many answers. Yeah, and I think the most popular guess is something like 700, but let's see what's the right answer here. And as we see that here we have an anomaly, and okay, it's not quite clear why this is an anomaly. And okay, you can understand that it's quite hard even to understand that we have something different from the usual sequence here. And maybe the reason that the widths of these peaks are a bit different, and the variance is also a bit different here, because as you can see at the previous slide, we have more distance between peak and we have more time on these peaks. Yeah, I suppose it's the time series of some sales, and we have two peaks at most of, okay, we have this peak, for example, and at each peak we have two sub peaks, and they have different nature here. Okay, another example, also quite challenging, and to be sure I forgot the answer to it, but okay, we will see later. Where do you think is the anomaly on this slide? Any ideas? Okay, so one guess is he's like there. Another guess is it's about 2000. And another guess is 2600. So this is the answer. Okay, and the answer here is there is no anomalies as a slide, so okay. It can be like this, and I suppose the last question, maybe one or two last questions here for you. Another type, another try. Where do you think the anomalies? So it's close to this guy, to this peak here. Yeah, you are right, but there was two anomalies. The okay, like peak value and like minimum too small unusual values. This degradation was lower than, I suppose that there is two small values here. and this bottom line. Okay, we can say that okay, there is something similar there, but maybe it's due to that we already observed anomaly here, and we have this like irregular pattern if this is a difference between this bottom value and this bottom value. But okay, I'm not sure because it's like okay, I don't know the exact nature of this time series, so I'm not sure actually. And you can try to guess at home what else in terms of context or other things you can try to do. And right now we have the last example here for anomalies to prove that it's like a challenging problem sometimes. Yeah, it seems like a peak. A good idea from Pavel. Okay, this maybe this small values for Aisha. And so let's see what's the right answer. We have one peak, and it was correctly identified from one of the students. And okay, what conclusion can we make? It's like very close to what we already made when we were talking about the challenges. About that, it's quite hard problem anomaly detection because we often don't know what we are looking for. And in this case, we are completely unaware of what we are looking for. And maybe after attracting an expert that will identify the anomaly. In this case, we can say what's anomaly and what's not. And on our own, without any additional knowledge, it's sometimes hard to identify anomalies, but we'll try. And we will start with a very general introduction of what approach we are looking for. We say that if we have time series or not time series, we say that our anomaly we are interested in is constructed of two steps. The first step is that we construct anomaly score from the data. So we have like input data each time moment, x, some features, and we have a threshold, and we say that we observe this curve as x, as the depends on x, and we have a threshold tau. And if anomaly score exceeds a threshold, then we detect an anomaly, and this is how it works. So we have two questions: how to identify S, how to identify tau. For S of x, we will discuss later. For tau, we mostly try to do something on the known anomalies or on the normal data. So like 99% of the data don't fall in the area of like anomaly values of the score. Or maybe we can say that all our data is normal and we have to select this threshold. So for all observable data, we have a value smaller than this threshold, but it's kind of risky approach. But okay, let's see what we can do about more complex SFX construction. Basic idea, if you have no labels here, if you want to do unsupervised anomaly detection, is to try to do something like this. We observe these gray points and we construct a model for a point. So we say that if we observe something at time t, or we have some features, we predict what other components is, and like what our generative model can produce at time moment. And so if we have a new observation here, we can try to apply this model to map it to this more regular curve. that is identified by the data we already have. And we can see the difference between the initial point and the mapping of this point according to our distribution. And we have this initial x and reconstructed x with a head. And if the difference is large, then we have an anomaly, because we trained a model that tries to capture all the data, and for all the data this difference should be small, because we trained this generative model with a lot of data. But if this guy is small, we say this like normal data. And again, what is small and what is large identified by a particular formula. And okay, if you want to write down formulas, we can, for example, try to do something like this. Suppose we have a set of points, and then so for each point we have x that belong to Rd, and we construct G models. The first model tries to reconstruct x1 from observations of all other features. xd hat is similar guy, but that depends on the first d-1 features. So we have these G models that we can construct within our data, because we just identify one feature as the target and try to predict it using a regression approach. And in this case, we can say that we have this anomaly score that we need to identify anomalies. And we can say that, for example, it can be the difference between our reconstruction and the true value of x. And this absolute value of the difference is what we are looking for. And so we can have like G anomaly scores. We can select the best anomaly score, and on the basis of this, make a decision about anomaly or not anomaly. So the very basic example, and quite good in my opinion, because it works well for many applied problems. Okay, but we can try to do better, because in this case we specified a particular problem on what a particular model that is our anomaly scores. We say that we can reconstruct each component of x using all other components, and we have like G independent anomaly scores. We can try to generalize this approach and say that we have encoder and decoder model, and the result of application of this after encoder, this combination of encoder plus decoder, is some x hat. And we want x hat to be close to x. And this is what we train on our learning data. So we have encoder here. After encoder, we have z. This is encoded sequence or encoded object. And we have decoder. And after application of the decoder, we have this x hat. And according to the procedure we used to train, according to our function, something like x hat minus x, we adjust the parameters of encoder and decoder for these guys to be close to each other. And if we manage to create good model, then we say that for normal data, the difference between x hat and x should be small. And in this case, we say that this is a normal data. And if this score is large, it means that we train it, our model is in different data. So this new data with high difference between x hat and x corresponds to some kind of anomalous behavior, and we can say that this those. So we can say that this guy is anomalous score. Again, if it's small, then the data is normal, and if it's large, then the data is anomaly. As it is, quite simple and quite fruitful idea that helps in many applied problems and in sequences data too. Two examples of encoder-decoder architecture is partial component analysis, if you want something simple and linear, and after encoder, if you expect that we will be working with figures over here. And so we don't need any labels. We just say that our loss function is a difference between x and z hat, And we use the normal data to construct such model. And then that's it. To identify the right architecture, we can abuse what we already have for autoencoders in the literature. We can start with usual autoencoder. Usually it's not a very good idea. Usually simple autoencoders that just minimize the difference between x and x hat is not continuous, no is interpretation, and no restrictions we would like to have for our model. And also quality also isn't very good. As we can see, when we go to embedded space for encoding of MNIST images for autoencoder, we have something very strange. In this point, all numbers meet each other and we can basically distinguish between them. It's quite typical. More advanced techniques for this is variational autoencoder and universal autoencoder. And okay, to be clear how many time should I devote to these two guys, please write ++ if you know everything about variational and universal autoencoders. ± if you know variational autoencoder, then you don't know universal autoencoder, and -- if okay, if it's like this, and -- if you don't know about both of them. Actually, a variational autoencoder was quite popular, and sometimes it provides state-of-the-art results. But during the recent years, a more interesting and better in terms of performance ideas the adversarial autoencoder. So I think that it worth to talk a bit about it and to pay some attention to variational autoencoder, because as I see, not all of you know about variational autoencoder for some reason. So let's go. Okay, for variational autoencoder, we say that we have encoder network that produces mean value and covariance matrix for our distribution of Z. Then, if we want to have this Z, we sample from normal distribution with this mu and sigma to get the latent representation. Then, using a decoder, we kind of sample, we have the Z and we apply it to decoder, and we have the Z variation of encoder. What's good about this approach? Why everyone is so excited about it? Why it's so good? We have basically two terms here. The first term is usual reconstruction error. So it's kind of how x and x hat are close on average. So it's something like this. But it can be, for example, log loss, also popular choice if you're dealing, for example, with photos. And also we have a second term, which specifies what we want to have in between, what kind of distribution we expect for these guys. And we say that we want the distribution to be close to canonical Gaussian distribution. So it's zero mean, unit variance, and this is our picture of that. And we can calculate Kullback-Leibler divergence. So our distribution in latent space would be close to this normal distribution that we can calculate. It works, and somehow we managed to construct very good looking examples, and we can see that okay, we have a better distinguishing between different types of numbers when we are trying to experiment with MNIST data, but we also can say it's not perfect. And it's not perfect because we have some like prior knowledge of what we expect and what we don't expect. And maybe we can try to apply this GAN paradigm to do this kind of things, kind of adversarial autoencoders. In this case, we again have two losses. The first loss is a reconstruction loss. It's similar to what I already talked, I suppose, a million times today. It's about the difference between reconstructed X and the initial X. And we have another loss. It is there to replace this Kullback-Leibler divergence. We say that we want to distinguish between positive samples and negative samples. So we say that we want to distinguish between this distribution, the object from this distribution, and the object from our prior distribution. So it's basically a discriminator that say that we want, okay, it penalizes if we generate that are very different from what we expect from our prior. And with this additional loss function, and with this usual retraining of autoencoder, generator, and discriminator, similar to what we have in GANs usually, we obtain a better representation for our data. So the basic idea is to replace like this difference between Q and standard normal distribution with the discriminator that can tries to identify the difference between Q and the initial distribution, and it has trainable parameters, so maybe it can do better. And so we replace, if you want to write formulas, we replace this regularizer with adversarial loss here. And okay, as suppose everyone is more or less familiar with GANs, so I will shortly describe what the GANs is and how can we adapt them to the anomaly detection. And okay, already we didn't discuss why do we need all these guys like autoencoders here in monitoring. So we say that, okay, we have this generator and discriminator framework, and we use generator to generate realistic images, and all objects or representations, and discriminators to distinguish between real and generated images. So if we improve discriminator, then we have improved loss function for generator, we improve generator, and so in the end we have a very realistic generator that's kind of generate very good looking money, for example, or very good looking images, or whatever we want to generate with it. And so we have this loss function, classic loss function for GANs, where we have discriminator and generators output. So we kind of generate fake data using this part. And we want for generator to be close to real images. So we minimize the score with respect to the generator parameters. And for discriminator, we want to have good scores for real data and bad scores for fake data. So we kind of want to maximize this loss for our discriminator that tries to distinguish the result of the generator. And so after training of this approach, we have better representations of the data. So let's try how it works for anomaly detection on the example of paper from 2018 on one class classifier in the thoroughly learned. Suppose we have, okay, do you have any questions? Okay, maybe I lost a contact a bit and can be a bit more advanced that we usually talked about. So, okay, if you understand everything and we should go on, please write down plus, or if you expect that you can try to work this one more time at home. And if you will understand something after this, you will be able to ask some questions during the next lecture. And if you are completely lost here, then please write minus sign, and we will try to see what we can do about it. Okay. Thank you for the feedback. It seems that you can try to go on. Okay, so let's consider an example, and I hope it will be more clear after considering an example what's going on. Suppose we have our autoencoder model training using images of penguins. A lot of them, and we have a large sample, and these penguins are very diverse, and so on. And so what we get when we train an autoencoder, adversarial autoencoder or variational autoencoder, does not make much difference now. We say that we have an input sample of penguin Then as the output, we will also have good looking image of penguin because we want our initial X and our images that we pass through after encoder. So this is after encoder output. So they should be close to each other. And as we train these images on penguins, we should be particularly good at distinguishing penguins. And for example, we can say that we can even denoise images in an automatic way. So if we have a noisy penguin, like here, we pass it through our after encoder, and in the end, we have very good looking penguin. And for outlier samples of an ice cream or some machine, we have very strange output because this is the data the model did not see during training, so it has very large error, at least if the images, okay, the training sample is tight and don't include something similar to ice creams. And also we can try not only see this from images, but also we can try to see this from scores. As we have in our framework a discriminator, we can look at scores of the discriminator here. And we can see that, for example, before after encoder discriminator score, that means that is the real image is quite high, and even bigger if we apply after encoder. So we can say that we are good at saying that this is a penguin, and if it's not a penguin, we see that these scores are low, and they're even low after application of after encoder. So big. So we can try to learn the model and use the decoder score as an anomaly score here. And the basic idea is that, okay, we have slightly different discriminator here, not only that we have inside of the strial encoder, but also we can try to train a separate neural network after application of after encoder and getting X prime to identify if it's a real or fake image. So it's kind of additional job we have here. So we have this gain loss for training of our, and okay, for training of our discriminator generator game, what we discussed a few minutes before. And we also have this reconstruction loss that also helps us to produce some meaningful results. So we add kind of a sink to our autoencoder, and that seems to be quite natural. Actually, we can try to do it in many different ways, but I suppose that this way is also good. I mean, it works good, and it's quite understandable why we're doing this and why we have this particular loss function. We can say that now we have some hybrid of variation after encoder and gain loss, or adversarial after encoder and gain loss, and it works quite good. And in the end, we have good generator here, and we have good discriminator here for the class, for the model we trained on. The architecture actually, in this case, we don't even need outliers. We train our model using only the normal data. We consider that all data we have is normal, and we train after encoder to reconstruct these images. Why? Okay, what we put into like this discriminator here? We can say that. We can say that if we have for this, we have good after encoder, then after application of this after encoder, you have X prime that is very close to X. And to improve this X prime, we want the discriminator of X prime should be high, should be still like close to 1, and should be identified as real images. This is the goal of our generator or after encoder. Generator after encoder here. And okay, for discriminator, it can try to do things like this. This is the goal of our discriminator that we put after encoder. So he tries to distinguish between X and X primes, real images and images produced by after encoder. And after training of both generator and discriminator, we have generator that can handle penguin images. So after application of autoencoder x and x prime is closed, and we can distinguish it with discriminator. But discriminator too learns something and can distinguish true x axis and fake axis. Quite good. So basically we don't need any labels here. We just assume that all data is normal. And in this case, we have a natural anomaly score. We have even true anomaly scores here. We can say that if we apply discriminator directly to the real images, and if the score is higher than chow, then we are happy that the image is real and it belongs to the target class. If not, we can say that it is an outlier, and we okay, we can cancel the threshold to get a good confusion matrix. Another approach is very similar, but we put to it not x, but x that we put as input of our autoencoder to get x prime, and for this x prime, we also should have high probability that this is a real image, and if this is true, then the probability of a real image is high, then we can say that it's okay, target class, otherwise it's an outlier. So we have these two ways to identify images. And again, we can try to see if it works or not. Or we use some scores, some data sets, some other methods to compare. And let's look at the table with scores of distinguishing between real and anomalous data. And we can see that, for example, for this second approach as anomaly score, and G error fix, if we run discriminator for as the output of autoencoder, we say that mostly we have better scores for detection of anomalies than all other methods do. We can have more details in the article, but basically this approach works quite good. There are a lot of other possible options. For example, we can try to apply several autoencoders in a similar way. We have two discriminators here to discriminate embeddings and to discriminate the output of autoencoders and so on. And actually some modern architectures, they are trying to combine them in various interesting ways and try to improve the quality of anomaly detection via this approach or discriminator-based approach and using complex semi-structured data as input. And they more or less succeed all of them. So, okay, let's go to the conclusions and try to figure out what we learned today and what I only mentioned, but I want to emphasize that this thing is also important. We have quite many requirements when we are trying to construct anomaly detection from scratch, especially if we have a low amount of available data. In a classic approach, we mostly try to construct some expert-based solution. I expect that what we are trying to do, the dependencies we are trying to catch, they're quite simple, or we can make them simple if we use the right features. In this case, we have simple workflows and quite good results, even if we have small amount of data or if we have small amount of global data. And okay, this is also about this point, but also we can try to solve this problem with neural networks in quite a good way. In this case, we try to do this representation learning, and mostly we use different options for afterencoders here. Okay, the state of the art right now, I suppose, is adversarial afterencoder, and there are some specific approaches for time series specific data, but okay, we don't mention them too much here. And so in general, we follow the rule I showed you today. So we construct anomaly score using deep neural network and select a threshold using few labeled examples or using normal data. Or what else we can try to do is to advance this field is maybe solve this change problem for threshold selection and also try to work to make it work better for sequential data. Also, and we will talk about this during next lecture, there is a completely different problem setting where I suppose there is little involvement of deep learning at all. In this case, we are not talking about anomaly detection, but we will work with very particular change point detection. In this case, we suppose that at some point we observe a change in distribution of data. And we want to identify the amount of change with as small delay as possible. So we are happy if we have this detection at this time. But if you have this delay, it's maybe unacceptable because the plane has already crashed or a nuclear plant is now like in a very dangerous situation and so on. So I want this delay detection to be small. And during the next lecture, we will see what we can do and what is not done yet. And I suppose that for time series data, there is still a room for improvement for in this particular area. So thank you for listening to me today. If you have any questions, you have a chance to ask me now, or you can later ask them in the chat. And I forward the microphone to my seminarist, Rodrigo, and he will give some details on what we are going to do during the seminar.
Yes, thank you very much, Alexei. So we will be having our seminar on the attention mechanism, and this will be basically in 20 minutes from now. So you will have 20 minutes break. Now is 5:04. We'll be meeting again at 5:24.
Okay, I will provide a record of the lecture after the deadline for a quiz, so you have more motivation to attend the lecture. Okay, goodbye to everyone. Good luck.
Have a nice day, Alexei.